So evaluate the performance of algorithm. So we have made one level of modification, that is we have kept only 4 cylinders samples. Essentially, under validation, we want to check how accurately the algorithm has predicted the mileage and compare. Just a minute, let me get to the right place here. So we'll check the visual comparison. So this I'm going to run all at once. Copy from here and I'm going to paste it here. I would like you to try out all by yourself to get a feel. Okay. This we have done before. We are redoing it. Shift enter. This is for the improved performance. We visually see that the values are coming pretty much a bit closer. Then we'll see the second type and we'll analyze what was our findings. So predictions within tolerance. So let's check how we are doing on this front. So we copy these ones and run it here. So this is going to generate like above 4cl out is output. Now below I have given a snapshot how that looks. So this has improved, not a lot, but somewhat, at least about 10% of more accurate readings, predictions. Now let's check on the root mean square performance. By regrouping data, what we find here, into a homogeneous group of 4 cylinders, we have improved the accuracy from 56 to 63% prediction and within 10% tolerance. Also, maximum deviation has dropped from earlier highest 65% to a new lower value of 27% of the mark. So the highest deviating point it has come closer. So we are improving somewhat, but we'll still do better. So we'll see how. So again, I'm going to do this RMSE thing, which we did earlier, and we'll see the values once again. In the end, we will take a stock how we fared. Shift enter. So this actually it went a bit higher if you see, due to insufficient training data. Now this is an important point you want to learn, because this experiment and doing multiple trials, what we are trying to do is how we are improving it. But everything will not work exactly the same way. Due to insufficient training data, the RMSE error in this case is marginally higher by 0.4%. Not 0.4%, but 0.4. That is 3. It has now increased to 3.39 minus 2.98 earlier. So let us see how we can improve this. Now improve the performance second approach. In the above trial, we found that the data became more homogeneous. These conclusions are important to learn from this. In the above trial, we found that the data became more homogeneous when we applied filter to select only 4 cylinder data. However, the training data also reduced to half the size. Smaller data sets resulted in insufficient training during machine learning. This is called underfitting. You don't give sufficient number of samples to the model get trained, so that does not give a great performance. So since we cut down the samples from 79 to this 40 something, so almost half the size, 41. So it was almost half the size. So that has deteriorated the performance. So let's see how we can make this better. Secondly, there was considerable variance in the data. So data also had a lot of variance. If you see the scatter matrix that we generated, there we see there is a lot of scatter in the individual values. So that also causes a lot of variation. It is now we'll discuss all of this in the end. So this has resulted in higher RMSE. Therefore, to check whether the accuracy could improve using larger data set, I have added some dummy data. So there are some scientific methods of doing this, but right now I have added some dummy data just to get a feel, just to tell you how we can improve by giving more data. So let's execute these instructions. So this is one more data set. You can just add some dummy rows to that. What I have done is I have actually sorted the data and took more of later part of the data. Okay, so the period that was covered by the data was from 1972 to 1982. So what I have done is to add some more samples, I have copied some rows from 80 to 80, from year 80 to 82, and which then that time maximum are showing Japanese ones, and they are more uniform and they are kind of better with fuel efficiency. So we have more uniform data and we have more samples now. So that is in a nutshell what I did to create the data. You can create similar thing or I can share this with you. So let's execute this instruction. I'm going to now load and prepare also in a quick shot. This is again we did earlier and we are repeating it. So I'm going to redo this. So just copy these instructions. We have done it earlier. Control V. So df4 dumb is having some dummy sample. That's why I named it as like that. This is the data frame. pd.read excel from my path. This is the Excel sheet with the added rows. I have created comparable rows almost equal to our original sample, but all with 4 cylinders. Skip row 0, again first row to drop the first row, and df4 dot shape. Shift enter. So this I have created sample. Earlier was 394. This one is 396, almost same, and 9 columns as before. So next instruction, df4 dumb is null dot sum. I'm going to save time now. Just copy the earlier instruction. We have done all of this earlier. So here we see in the horsepower there is some bad data. So we're going to visualize that. We have visualized this and we're going to remove this. Now to remove this, we are going to change this by fill na dot mean and then create the sum once again. So this we have seen earlier. I'm only doing something we did earlier once again. So copy paste and run it again. Shift enter. So now I have corrected all of them to 0. So all data is good. Now set up the data. So like the above one, we'll also visualize this once. I'm going to create one more scatter matrix plot just for our visualization. So this is a standard process. You must not skip this just to get a feel. But you can, while you do this, you take a look. You try to learn how those things are, the various correlations between variables. This scatter matrix basically is for correlation. So here we are seeing some scatter, some more concentration of some data. So similar pattern like we have seen earlier. Here are the histograms. So where incidentally what you should remember is when the column and row are same, MPG versus MPG, there we have the histogram. So all this we are seeing here. So each histogram and each bivariate variables. Not all variables correlations are important. We need to stay focused on what is our predictor variable and what are the impacting variables we need to look at. So again we set up the model like before. These are the same bunch of instructions. We're going to re-execute. Set up the data, define and train model. So here we have 80 rows. Earlier we had 79. Here we have 80. So it's almost comparable. So all are 4 cylinders and all are more uniform kind of. Let's see how this performs. Define and train model. So regression model we're going to define and coef we're going to generate. So I'll add one more row here below this to run this bunch of instructions. Control V, Shift Enter. So these are the coefficients. Now we are hoping for a better output. Let's see how it comes. Predict output. Y pred equal to regression model dot predict x test. So same process again. And pd.dataframe, we're going to create another data frame, actual versus predicted, and we're going to compare the results. Control C, we're going to predict the output now. So now visual comparison. So let's see if this looks better. Just to get a feel, visual comparison. Let's do the visual comparison now. Pretty close. They are looking much better now. Now let's see how they are faring on the other fronts. As expected, by increasing the input samples, we have substantially improved the prediction within tolerance. Let's see that now. Now this is an important thing for us to observe and learn from. So this is now executed. Now what we see is the accuracy is very much improved now. Why it was improved? Because all the data is homogeneous and we have given more samples, right? So we have percentage 22.5% are off and 77.5, nearly 80% have come closer. Now if we have more, you can even extend this concept to more closer and more homogeneous data. We'll discuss this in the end. So how we can do better and better on this performance. So root mean square error, let's see how it is. So we are a bit better on this front also. Earlier the very first was 2.98, then we improved it, we made it worse by cutting down we are giving insufficient training machine learning samples. So that went to 3 point something by 0.4 higher. Now it has come to really in good values. We are getting 2.78. So again it has become 2.78. So now this is most important. Let's come to the conclusion and roadmap for future improvement. So is this all we can do as improvement? Not at all. Rather, this is only the beginning of the infinite opportunity of handling real life use cases. Note that by better grouping of data and then by adding sufficient number of samples, we reduce the highest error percentage from 65% max to 27% max to 17% max. Then this was the highest deviation from the between predicted and actual. So that we reduced considerably. Improved the number of accurate predictions by initial low 56% up to 63% and then finally 78%. So which is pretty good. Improve RMSE from 2.98 to 2.78. There is a lot more that can be explored. For example, increase the number of samples. We should remember machine learning performance improves by large number of samples. Try for uniformity of data. Like for example, we get larger number of US models. Could we get data covering a year or two? We have 10-year data. So maybe if we have narrow range, there's a better chance of predicting closer. Then can we have a single model? We had whole lot of models that we are putting in the data. So maybe we could try out for single model. Another area to explore is use of scaling to make the data same order of magnitude. So this needs some explanation. So if we just scroll up, let me take you up a bit. If you see, this predictor and coefficient. If we look at this table, we see that 0.02%, 0.06%, these are the importance that model learning is indicating as how much a variable is important. Now you see here that the year is giving 1.0006. Then these are the importances it has given. So actually what we should do is the numbers, basically as we discussed, the machine learning model only understand the numbers. So the order of magnitude matters here. See, in the case of weight, it is the numbers are 4-digit numbers like 2000, 3000 kgs, right? Then in the case of MPG, we have like in the tens, like 30, 40, they are the mileages. So year is 77, 78, these are the numbers. If we see in the machine learning, the standard processes, normally if you bring all this to the same scale, then the machine learning model will learn better. So these are the things that can be explored in detail, but I'm just giving you pointers here, but these are the things that can improve. So scaling is one of the things that can go on. Then scaling, okay. Then consider additional parameters to classify data like distance traveled, time taken, age of vehicles. So we have taken only weight, whatever was available. So this list can weight and displacement and horsepower. These are the factors we considered, but there can be few more which are actually impacting. So this is how we solve the real life problem. The list can go on. On the final note, we could also extend the application for a car manufacturer or some third party application to conduct large number of tests and say in an area based or city based to advise more realistic estimates to the customer on the mileage on the basis of road conditions, traffic jams, signals. So all these factors also contribute in terms of time taken and mileage. So with this, we conclude our discussion here.